Okay, I had some comments on my recent video about the PLL theory, so I thought I'd just expand on it a little bit, because a comment was that I hadn't gone into the loop filter aspect of the PLL design, which is a fair point. I didn't actually go into that at all. I simplified that section of the video. Basically, where I say that the PLL outputs a voltage to the VCO, that's not exactly correct. It outputs pulses through a filter to the VCO, which then that filter is what smooths it out and turns it into a voltage, a smooth voltage. Alright, so to try and explain upon that a bit more, here is a pulse diagram for the MC145-170. Alright, so this is the output of the PLL, the phase detector output, relative to what it's seeing on its reference oscillator input and the frequency returning from the VCO. So ignore these other stages for now, just look at these first ones. So if the feedback from the VCO is lagging the reference frequency, so in other words the frequency is too low, the phase detector in this case is a tri-state, will output a positive pulse to increase the voltage to the VCO in order to try and increase the frequency. This particular PLL's got a tri-state, so it's actually, it will do positive pulses, negative pulses, or stay high impedance, where it's basically not dragging on the VCO filter or the loop filter at all. So again, it shows that pulse width there is relative to the difference in frequency between the reference and the feedback from the VCO, the F in frequency. So it's relative to that difference. This is what's known as a type 2 VCO in this case. Type 2 phase detector, sorry, not VCO. Which means it determines whether it's leading or lagging, and it reacts accordingly. A type 1 is just like an XOR gate, and it will actually just put a pulse out regardless whether it's leading or lagging. You can't really tell. That's where it's critical to actually make sure the frequencies are within certain ranges and stuff like that. I think normally you don't tend to see that sort of thing anymore. Yeah, so if the VCO frequency is lagging the reference, it will try and increase the frequency of these pulses. If the VCO frequency is leading the references and the frequency is too high, it will try and retard that frequency. Alright, so it will actually put a negative pulse out to try and take voltage out of the filter in order to push it back a bit. And when they're in phase, it doesn't really do anything. Okay, this is another alternative output. Is it does pulses if it's lagging, or pulses if it's leading. All right, so it's individual outputs instead. That's another way of doing it. On this particular PLL's got an option on it, but most people don't tend to have that. Well, most radios don't tend to have that. And you can also see here that the lock detector pulses are relative to if there's an error or not. So if there's an error in frequency, the lock detector is also active. So if you never get a lock, the lock detector is always turned off and the radio doesn't work. Which is why when you get right on the edge of lock on a VCO on a radio, where the VCO is almost on frequency, it's really close, it's there sometimes, you'll see that the radio lock flicks in and out really rapidly. Maybe the TX light will flicker on and off and that sort of stuff, or the RX light will, depending on how it's configured. You know, that's when that happens, when it's right on the edge of lock and it's getting it sometimes and sometimes not. Obviously, its pulses are extremely fast. I mean, that's each waveform. You know, depending on what the references are, like kilohertz frequencies. So generally, so yeah, that's how that part works. Down here somewhere are some filter examples, which are often used actually. They're very like what we see in radios. So the filter here is a typical filter. So the phase detector output comes through a resistor, through a capacitor filter. Now the filters actually take out a lot of our high frequency harmonics and stuff like that, and smooth it out. So it's called a low pass filter, but it's basically smoothing it to DC effectively. That's what it's really doing. It takes out a lot of high frequency content. Now sometimes there's actually a second capacitor on the side, as you see in the diagrams in a minute, and that's to take out the high frequency and actually to make it easier to achieve a lock. So these resistance values are chosen based on formulas. I think these are relative to it. I don't have a clue what any of this is. I really don't understand any of it. So I'm not an electrical engineer. I'm just a hobbyist who's figured the stuff out as I go along. Yeah, so this filter network here is basically what smooths it out to the VCO. So those pulses come in, they charge the capacitor up, and because of these resistors, or in this case just that one resistor, they charge it and then discharge it at a controlled rate. And because the resistor here is tending to discharge through the VCO to help push that voltage up, rather than dropping back through the phase detector. But when the phase detector pulls negative, it's trying to discharge through this way instead to drag that voltage down. So that's why it's done. This is also the separate output option here, where it's got one pulse for negative, one pulse for positive, to control it through that system. So let's look at a circuit diagram. Let's just get rid of this. This is one example. Cable 148 GTL-F. This is a better diagram to try and see because it's nice and clear, but well, it's well printed. So here's the PLL MB8719. Phase detector comes out of pin 5. It's got this little filter network in here, and an amplifiers in here. So it's got two phase detector amplifiers and filter systems. The signal comes out this path here. Right, so it's TP9. That's a test point for the VCO voltage, which is actually the phase detector voltage. That is a pull-up resistor just here. Now, what that is doing is biasing the pulses, so it will pull it up a bit, and it may actually, in some cases, cause problems if the phase detector is not being skewed in one direction or the other. So if it's too neutral, it may actually go out of sync with the incoming frequency and actually have trouble locking. It will go out so far out of phase it can't do it. So having a pull up or pull down resistor, depending on the radio, helps to pull the phase detector in one direction to make it bias, as it were, in one direction, which helps it to get lock. Sometimes it's literally just a pull up or pull down. That's all it is. Sometimes it's not necessarily just that aspect. It's not necessarily just trying to get the phase detector to work harder. It's about actually controlling the voltage going in as well. Sometimes it's not just that. So it might be you've got a phase detector which is putting mainly negative pulses out, and you need a positive pull up to balance it out so you get a voltage coming out as well. That's the other aspect too. That's it depends on the chip really, but generally there is some kind of biasing involved. So there's that resistor there, which is in that example diagram I showed you just now. So that's feeding through that resistor. Here is the capacitor network. So as the second example, effectively there, resistor and capacitor series, and there's another capacitor next to that in parallel. That takes out the higher frequency, and this takes out the lower frequency stuff, smooths that out. This resistor value can be adjusted to affect the responsiveness of the phase detector signal. So how much of the pulse it smooths out. So if you actually measure that on an oscilloscope, you can actually see the pulses in some cases. And if you're seeing too much oscillation in the voltage at this point, you might be able to actually just tweak this and change it a little bit and improve the frequency. Especially if you're doing like a PLL replacement or something, you might find the phase detector output from the PLL is slightly different to the original, and it doesn't quite work the same way. You might need a bit of tweaking. And over here's the VCO, right? So I'll go to another diagram. This is the 29 limited, code 29 limited. Slightly different layout, but works pretty much the same way. Let's just get this down a bit so you can see. Pin 19 phase detector output. Well, the amplifier output. The actual phase detector is over here, pin 17. That's a little amplifier in there. A bit more filtering. You have to be careful about these capacitors because they can actually fail. I've had incidents where the capacitors in the phase detector circuit here have failed and caused all kinds of weird problems with locking, not locking, and only on certain frequencies and stuff like that. So if you do get weird things like that, you might pay to check these capacitors because they can go wrong. Anyway, so it comes out, and this is laid out slightly differently. This is a pull up, and there's the filters, like filter capacitors right there through that resistor. So it's slightly different layout, and this bit here is actually a VCO. There's a reactor diode, and this is the VCO oscillator IC, and it's also like a mixer and stuff as well, but we won't go into that. So yeah, it's the same thing but different, right? Again, these values are all tuned to suit the chip pretty much, and what the pulses are like coming out. There's another one, MC148, MC Cobra 148 GTL. This is the older style, the original 148. Again, here's the phase detector coming out, network for the filtering, amplifier stages. There's that pull-up resistor there again. Comes through. There's that resistor there. There's the test point. There's the filtering. All right. There's the low-pass filtering. So that is all, very similar across all the values, all at the same way. The only thing that might change maybe is the values, but generally they're all very, very similar. Okay, so I thought I'd cover that and try and show that, yes, I simplified the previous video to say, look, is that a voltage comes out. Well, yeah, I'm trying to simplify it, but so I thought, okay, I better expand upon that a little bit, because that filtering and that the way that pulses and the actual phase detector output works, I suppose I probably should have included that in the previous video to explain that function. I did, eliminate that just for the sake of simplicity, but I think, well, actually, no, I probably should have included it. Based on a comment I got from Lazarus, yeah, Lazarus it was. So he said, I basically omitted that part of it. So, okay, yeah, I should put that in. So I thought, right, I'll do another video and cover the function of the phase detector and actually how that outputs, and that loop filtering is quite important, because if you do have issues with any of these capacitors, it may stop your loop from locking, because these are supposed to filter out the high frequency content and smooth out into a DC supply into here. So you've got these pulses coming in here, those little square wave pulses or sine wave pulses, maybe, usually square wave. Depends on how all this lot's working, but that's no good for generating a frequency here. That has to be smoothed out, otherwise you get oscillation within the VCO as well, like a secondary oscillation. So it'll get like a warble on SSB, for example. The frequency is always changing, or you can hear noise and receive and transmit, where the frequency is always chirping around. That's the effect you can get from poor regulation in here or in here, mostly from this part. So if you do get that kind of thing, it's worth looking at this part of the circuit, because that's likely where the fault lies. Anyway, so yeah, I thought I'd cover that, and hopefully that's filled those gaps in. So I'm not an electronics engineer, I'm just a hobbyist that has been playing with radios for 30 years. So yeah, I just figure things out as I go, and like you guys, I've watched videos and read books and stuff like that to try and learn more and educate myself in this area. So hopefully passing on a bit of my understanding will help. There's lots of other videos out there on various aspects of electronics. Don't just take my word for something, I could be wrong, but I tend to think in, I don't know, layman's terms. I don't tend to be too technical about stuff, as it were. So yeah, hopefully this aspect of the filter system, which is important, as definitely true, that helps to improve the understanding of how it works. It isn't truly a voltage that comes out, it's pulses, and if you measure the voltage, you will see an average, but your multimeter or whatever, if you're not using an oscilloscope, won't show that it's pulses. It will show an average, and it's not necessarily accurate. At this point it will be fairly accurate because it's been smoothed, but back here it won't be. So anyway, that's I'm going to say, because my throat's going again. Have a good one, give us a thumbs up if you like it, usual stuff. If you don't like it, tell me why, I want to know, and let me know what you think. Have a good one.